Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very fortunate to be joined by Professor Stephen Pekar from Queen's College in the City University of New York. Stephen is a guest at the SETI Institute, courtesy of the Integrated Ocean Development Program, which sponsored his travel across to us today. Steve is a graduate of Queen's College himself, and also he did a PhD and Masters in Geology at Rutgers University. And he has, in his career, three types of projects, all involving to some extent Antarctica. His first area of research is global sea level and ice volume in Antarctica, using lithophases, that is looking at biomarkers and stuff like that to date events in Antarctic history, which I'm sure we're going to hear a little bit about during his talk. He's also a member of the Andril Antarctic Climate Team, looking at drilling into Antarctica. And he's also got an interest in warm periods in Earth's history, in the Miocene and in the Pliocene. And he looks at those using stable isotopes and tries to determine a little bit about Earth's climate. And Earth's climate is exactly what he's going to be talking to us about tonight. As the title of his talk suggests, past climate and ice volume changes in Antarctica, looking back to our future. So if you'll join me in welcoming Steve.
Well, I want to first thank Adrian for inviting me and the rest of SETI. I've just had a wonderful day today, meeting many of the scientists here. And part of the reason is because when I was younger, teenager in early 20s, I was an avid amateur astronomer. I had my own I took on 3 paper routes to get a big telescope and was looking through the stars. But, you know, I lived in New York, so not too many stars, but the planets were good. And subsequently, long story short, I became a geologist, and I study today climate changes of the past. And when we talk about climate changes of the past, when we're talking about more than 1 million years ago, most of our records, most of our understandings comes from deep sea drilling. And so, since I was invited by the Ocean Drilling Program, that's what I'm going to emphasize on how first of all, we understand climate changes from tens of millions of years ago, as well as some of the expeditions that we've done. And so today, I'll first start off with what is the Ocean Drilling Program? What is it? What does it do? So on and so forth. And then summarize on how we estimate ice volume changes from tens of millions of years ago. How do you do that? And most of the time, we're doing it from records from thousands of kilometers away. Okay? And I'll talk about those. And then I'll talk about how big the Antarctic ice was during times of elevated CO2 in the atmosphere. And what's so interesting is, like, if you go back at the ice cores, many of you know about the Pekar and Vostok ice cores, they go back 400, 800,000 years, hundreds of thousands of years. But yet, CO2 never rises above about 300 parts per million. Okay? Today, where is it today? About 395, and it's rising quick. We haven't seen this level of CO2 in the atmosphere in the last 3 million years. So what we've done in the last 150 years, Mother Nature could not do in 3 million years. But if you want to go back to what we expect at the end of the century, you've got to go back tens of millions of years. And that's the story I'm going to talk to you about today. And then finally, talk to you a little bit about some of the sea level and ice volume results from the Ocean Drilling Program expeditions. But since I'm at SETI, okay, I have to tell you this. I saw this on the Huffington Post. I don't want to break anyone's heart at SETI and everything, but, it's been confirmed. The White House has said that there are no aliens have contacted Earth yet, okay? It was 2 days ago. I couldn't help this. And so and when, and the most depressing and sad thing about this whole thing, for us people is like, there's no Area 51. So anyway, I saw this, I couldn't help it. But anyway, let's get back to our passions as opposed to Area 51. Geology is a little bit like exploring outer space, and that we explore, us geologists, we explore life and places that are quite different from what we have today. For example, the Earth is over 4.5 billion years old, okay? 4.5 billion. I get annoyed waiting for the subway after 15 minutes. And if you just go back 2% through Earth's history, 2% through Earth's history, okay? This is what the Earth looked like. And so if you were in a spaceship looking down at Earth, okay, you'd be hard-pressed to even recognize any of the continents. And I was looking at it today, and I said, okay, there's Madagascar, I can see that. Greenland looks pretty Greenland-like. But North America, no Florida, Inland Sea, South America, maybe the coast of Africa, perhaps. Asia and Europe look very different. And that's just 2%. And then if you want to talk about the fauna, this is Spielberg territory, okay, in terms of animals and sea life. If we go back just 6% back, 260 million years, you're going to recognize none of the continents, period. Why? Because all the continents were together in a huge landmass called Pangaea. So I was talking to a scientist today, he's looking for planets outside of the solar system. An Earth-like planet could look like this, okay? This doesn't look like Earth. And the animals that were on our planet 260 million years ago, non-recognizable. Again, Spielberg territory. And so we have a few things in common in that regard. That we're basically boldly going, in my case, where no drilling bit has gone before. And and here, it's probably where no radio telescope has gone before, I guess. So, what is the ocean drilling program all about? Well, it's been going on for decades. And it's gone through 3 iterations already. And the first one was the deep sea drilling project. It started in the late 60s. It was really there to basically prove plate tectonics. And it did it. Because it was a drilling ship, went into the middle of the ocean, dynamically positioned so they can keep drilling over the same location for a long period. They traveled, actually the ship, the Global Challenger, went over 600,000 miles. Okay, for us astronomy buffs, that's more than the distance from Earth to the Moon, in fact. Okay, recovering about 57 miles of core. That's a lot of core. And it showed many different things. Proved plate tectonics, but we needed a better drilling ship. And so the next iteration, started in the 80s, was the ocean drilling program. And this used the JOIDES resolution, a much bigger ship, a higher technology. Many more countries were a part of this. This was in the great tradition of when the world signed the Antarctic Treaty. This was cooperation. I mean, this is kind of an anti-reality TV, okay? In reality TV, everyone's competing. Here we're cooperating. They're trying to win things and beat somebody. Here we're sharing information. This is the way scientists work, in fact. And they were able to drill down to below 2 kilometers below the sea floor, recovering records up to about 160 million years ago. This is a map of the sites from the DSTP, and with the numbers, this is just the number of the site. Every site's got a number. And this is putting them all together, ODP, DSTP, and it looks like a lot of cores, especially with those numbers there. It's like, do you need to drill any more? Hello, But you start noticing huge parts of the ocean, especially like in the Southern Ocean, of course the Arctic Ocean. You can't see it here, but right along the coastline in the shallow waters, we can't get the drill ship in well. As well as we also can't drill very deep to get into the really interesting parts for like plate tectonics, to get into subduction zones. We just don't have that capability. And so what came out of this, for the next iteration that started in 2003, was IODP. Not changing too much, it's just an integrated ocean drilling program. Integrated because we keep the JOIDES resolution, so we can drill deep in the ocean. But if we want to drill into like subduction zones, we needed a bigger ship with better capabilities and technology. And the Japanese built the ship that we call the Chikyu. I call the Godzilla ship because this is huge. This is much bigger than that. And then mission-specific platforms. And mission-specific is where we can go into the shallow waters with a jack-up rig, or we can go into high latitudes where there's lots of ice, and we can use icebreakers to drill and get sediments for the first time in these regions. And so there's basically four major themes. We have climate and ocean, which is what which I work on, and we'll talk about that. But we also talk about the biosphere frontiers, where they're finding life just not in the sediments, but deep in the earth. Meters, tens of meters, hundreds of meters below the sea floor. And in fact, I've heard one scientist say that there could be more biomass in the deep earth than actually on the surface of our planet. Incredible stuff. Frontiers right here on Earth. Earth connections, we're talking about, in this case, we're talking about like mid-ocean ridges, for example, the hot fluids and the rock, how they interact. And then, of course, the Earth in motion. And that's where the Chikyu, that huge ship, comes into play, where they've been able to drill deeper, getting actual rocks and fluids from within subduction zones. And after what happened in Japan this past September, the need for understanding how earthquakes happen, why big ones happen in other places, it's just small ones, is so important. And so I'm going to focus on the JOIDES resolution because that's the ship I've been on. Actually, I met a scientist today who actually was also on the JOIDES, and I said, wait, you're at SETI, what are you doing on this ship? And it's a great story. But anyway, it's a big ship. Okay, it's about 12 school buses long, almost 500 feet, and it's tall. It's over 200 feet, which would be like a 20-story skyscraper, in fact. And this is the drilling rig here. So we have this pipe. I will show a little close-up, looking up. This pipe is about 100 feet long, and inside the core barrel, we have inside this pipe, we have a core barrel that goes in, and those are about 10 meters, about 9.5 meters long. And this is the drill bit here. Okay, you don't use this trying to build carpentry, let me tell you. So it's a drill ship. Okay, but it's a lot more than that. It's actually a floating research center. It's got stacks of laboratories about 4 floors high. And what they're there to do is to collect cores. Cores from whether it's volcanics and mid-ocean ridges and subduction zones, or sedimentary cores from the deep sea. And I'm going to show you what these are all about. Because these cores contain the rocks, the sediments, the fossils, that we can do things. So we can look at the rocks or the sediments, we can look at the fossils, and then we can do the chemistry on these rocks and fossils to figure out what's happening in climate going back tens of millions of years ago. And so what's going on here is that we have 30 scientists on the ship. We have 2 12-hour ships. So we have 15 scientists doing the same thing for each shift. So there's 15 different jobs going on. So you kind of go, how can you figure out 15 different things but to do on some sediments? Well, we do. Okay, everything from looking at the different types of fossils, looking at the sediments, looking at the physical logs, whether it's using gamma rays or velocity and so on and so forth. This is a scientist here looking through the microscope. Here's some sedimentologists, and this is what we do. And it's right now the IODP has 22 countries that are working together. So it's cooperation. So this is one of the few places where we have this. The national posturing is gone. Okay, this cooperation and sharing of data. And so when it comes to ocean drilling program, we own past climate change. Okay, I have to do a little bit of boasting here because, hey, And first of all, we were the first to develop continuous cores going back hundreds of thousands of years. And also contain continuous records going back for the last 100 million years. In fact, when we're talking about the times of the dinosaurs, the height of the dinosaurs, and we got ocean temperatures, global climate estimates. We've developed new proxies, so we can now estimate what the CO2 is like going back tens of millions of years for the first time. And then finally, also identify major shifts in the global climate regime. And I don't have time to go talk about some of them, but like, for example, I have a little PTM here. That's an event that happened 56 million years ago. We had a runaway greenhouse world, and the result was that temperatures warmed up where in the Arctic Ocean, surface temperatures could have reached into the low 70s. Now let me tell you something. In New York City, I'm a New Yorker, a late August day on Jones Beach, we'll be lucky to get to the low 70s, okay? This is the Arctic Ocean. And in fact, there's some estimates for sea surface temperatures off in New Jersey or New York where they thought it was like in the low 90s. Okay? We don't even know if that's a summertime signal. We hope that was a summertime signal. Otherwise, it was pretty damn warm for those lemurs, let me tell you. And so, but still, this is all fascinating. Isn't it fun? Isn't it cool, right? But why should we really study and collect all this data from the past? I mean, really. And the reason is because the future is data poor, okay? Quite poor. Unless you have a crystal ball. And if you do have a crystal ball, there's this mega lottery that I want to play next week, okay? So we need the past to try to understand the future. And we have great analogs for that, in fact. And so there is an importance for understanding past climate change. Most of us are all on board, about that climate is warming today. It's due to society and the world, and it's going to impact society and the way we live. Okay, and it's understanding the past climate changes that we're going to be able to make better predictions about the future. So I'm not going to bore you with all the reasons because I'm sure most of you guys are on board. But just real quick, the y-axis here is CO2 in parts per million. This is from 1000 AD to present, and you can see that CO2 is a flat liner through the last 1,000 years until we get into the Industrial Revolution, and then it starts taking off. And it's already warmed, okay? But this is just the tip of the iceberg, because if you go into this century here, this is what we're projecting. And right now, like the lower estimates here, okay, this is like if all the politicians got hit by lightning. Not that we want them all, but maybe a few. But anyway, if we really changed our tune and switched over to green energy, we may be able to keep it to 550. But right now, we are just, and this is from 2007, we are right on pace before going up to 900 parts per million. Okay, because we're still doing the business as usual model. What does that have to do with temperature? Well, this is global temperature. So this is the departure from zero would be departure from average from the 1990s. This is from 1000 AD to 2000. And the red is the best fit. This is the error bars here. You can see that it's basically a flat liner, not cooling until the last 150 years. And this is what the climate models are expecting based on the greenhouse gases. And so again, we're trying to shoot for 2-degree warming, but that's probably not going to happen. But we're on this trajectory going to about 4 degrees Celsius. And I'm going to show in a couple seconds that we haven't seen this. Civilization has never seen this before. Homo sapiens have never seen this before. Hominids have never seen this before. And we get upset if there's a drought for 1 year. So, and also another thing, let me just tell you, we're changing the atmosphere extremely rapidly. And in fact, the last time the atmosphere changed more rapidly than today, okay, was 65 million years ago. What happened 65 million years ago? An asteroid hit the Earth and wiped out the dinosaurs. Okay, poor dinosaurs. It was a very bad day for the dinosaurs. And let me tell you something, guys. It wasn't the dinosaurs' fault. Okay? And on top of that, they couldn't do anything about it. In this case, it was we caused the problem. We can make the solutions. And so, but again, void study sea level changes and stuff like that. It's not a big deal. We're talking about a meter or so, And so this is a representation of New York Harbor if all the ice melted. And if all the ice melted, sea level goes up around 70 meters. And it's up to about her shoulders here. Now, if anybody ever saw the movie that Spielberg did, Artificial Intelligence, about the little robot boy looking for his mother, it's in the future and all the ice melts and sea level goes up. And they have this futuristic helicopter flying in over New York, and they have the water, the sea level up to here. And I'm watching the movie, and I'm a scientist, and so I nudge my wife and I go, honey, it should only be up to here. And she goes, you're the only person who would know this, Steve. Just go watch the movie, But anyway, it should only be up to here. Okay, by the way. About 230 feet. So, but and if this is what the coastline would look like if all the ice melted. But I don't want you guys to go home tonight and go, oh my God, this guy from, this professor who came to visit SETI said, this is what we're going to have. Because, we're not talking about Orlando or New Orleans being in trouble. We're talking about Memphis being in trouble. But this is when this would take thousands and thousands of years. Okay? Geology changes. So we don't need this. We need the ice sheet, 5% of the ice sheet to melt, which would be 3 meters, which would be catastrophic. Okay? And those are some of the upper limits of climate change estimates right now. And so another thing, before I get, this is getting a little bit depressing, right? But just one other thing I just want to mention is that CO2 dissolves into the ocean. When it dissolves into the ocean, basically, through the chemical reactions, becomes a weak acid, reducing the pH of the oceans. And basically, it's impacting already the reefs. And this is what a paper from 2008 talked about. That when we reach 450, the reefs would go into rapid decline. And by the time we get to some of these upper levels, we're talking about a catastrophe for one of the most beautiful biosystems that we have on this planet.
Was that parts per million in the ocean or in the atmosphere?
This is in the atmosphere. This is what we're expecting. Before any level for the atmosphere, it'll dissolve into the ocean and then form a weak carbonic acid. And so just one more last little thing. Most of you guys are already on board with this, but I like to show this anyway, is that the debate that we see on TV today about climate change is basically a non-starter for the climate scientists. For climate scientists who publish in peer-reviewed journals, over 97% of them accept that climate change is happening and it's due to us. Okay? And so so it's 97 to 3 or 98 to 2, whatever. And basically, just imagine, just say you start feeling some pains, okay? And you go to the doctor, but you don't go to one doctor, you go to 100 doctors. And 97 of them say, yo, you got a life-threatening illness, you better do something about it right now. But 3 of them say to you, well, I don't know about it. Maybe we should wait a little bit and hang out. What would you do? Okay? And that's where we're at right now with the climate change debate. Okay? And that's all I'm going to say. That's my little political thing. So let's go into what the geologists say about climate change of the past. Well, the last time we saw a 1 degree warming, or actually it was about 0.7 degree warming, was about 6,000 years ago. Okay? And it wasn't because, the people in Mesopotamia were driving around in little SUVs. Okay? No, it was because the Earth's orbit changes from a near perfect circle to a little bit more elliptical every 100,000 years, and its axis wobble, it goes like this, from 22 to about 24 and a half, depending on 20 to 40,000 year cycles. And this is why it was like that. It's a little bit warmer, not because of the CO2. The last time we saw a 2 degree warming, we haven't seen in 125,000 years. And again, it wasn't because the cavemen were driving around in SUVs, unless you think the Flintstones was a documentary, of course. But, Palin thought so. But anyway, I didn't say that. And again, it was because of these cycles of the Earth's orbit, as well as its axis changing. The result was part of the West Antarctic ice sheet collapsed, as well as the Greenland. Sea level was up about 20 feet at least. There's a new study that says it could be closer to 25 to 30 feet higher. Now, the last time it was 3 degrees warming. This was due to CO2. Okay, CO2 estimates for about 3 million years ago was about 400 to 420 parts per million. We're approaching that right now. The reason why we don't have a 3 degree warming already is because of thermal inertia. Okay, for those guys, who have, remember the old refrigerators or the college small refrigerators where the freezer would fill up with ice? Okay, and you unplug it, you open up the door, the ice doesn't melt it instantaneously, right? You have to put in the pots of hot water and the whole 9 yards. Thermal inertia, same thing here. The Earth is warming up. And so this was about 3 million years ago. And 3 million years ago, we had like little hominids jumping around at that point. Now, the last time that CO2 was as high as what we predict for the end of the century, we talk about 25 to 50 million years ago. And back then, the Antarctic ice sheet was completely dynamic, and sea level was rising up and down 100 feet at least. Now, this would still take thousands and thousands of years to happen. Okay, but this is the trajectory that we're heading into as we put more CO2 into the atmosphere. I don't want you to go home and go, oh my God, sea level's going to rise 100 feet. No. It's not going to happen today, tomorrow, this century, maybe not even in this millennium. But I'm just showing you what us geologists know what happens when you put CO2 in the atmosphere and the Earth is allowed to reach equilibrium. Okay, so let me give you an idea of what I'm talking about. This is thousands of years ago, so this is 800,000 years ago. This is the Pekar core, ice core from Antarctica. And I'm just going to point out, it's called Bini Oxide in red here, and you can see that it goes up and down, but it never gets above, barely gets to maybe 300 parts per million in the last 800,000 years. This is what I'm talking about. We haven't seen today's levels, which is approaching 400, in millions of years. But that's just the tip of the iceberg, because, like I said, it was 3 million years ago since we have these numbers. If you want to go back to 450, 500, 700, we have to go look at tens of millions of years ago. The last time was 900 parts per million, was 40 million years ago. And back then, the Antarctic ice sheet was basically non-existent. It was small, ephemeral in nature, up in the plateaus. And this gives us an idea of what a long-term record. So this is millions of years ago. So this is 60 million years at the bottom here. This is CO2, and this is a very low resolution record because this is a new technique that's still being formed here. And you can see that, but generally the CO2 decreases and becomes a flatliner by about 20 to 25 million years ago. On this side of the record here is sea level, okay? And sea level here is a combination of ice in Antarctica, because there was no northern hemisphere ice until about 3 million years ago. And also what's called something called techno-eustasy, which is basically if you basically in place like a big igneous province in the middle of the ocean, you displace water, sea level rises. So there's also that component too. But you can see this general, where it was much higher, decreases, becomes a flatliner, and if you follow the purple, because that's the calibrated, it only decreases to today's levels in the last 3 million years. And this is just showing the last 3 million years. The last 2.5 million years has been the coldest it's been in the last 200 million years at least, okay? But we've had glaciers basically reaching New York City as recently as 20,000 years ago, okay? So you can see this. Higher sea level, less ice, going to a generally colder and more ice situation. And let me do a little close-up in here, what this is all about. Okay, so this is CO2, and this is millions of years ago, from 16 to 45 million years. This is the general trend. This is the best estimate in the black. The red bar is what we expect for the end of the century. Today's number is around 395. And this is sea level, okay? So this is a record that I put together with another professor here. This is from Miller et al. And when sea level's higher, there's less ice, right? When sea level is lower, there's more ice. And you can see that CO2 makes a general trend. It's low resolution, mind you, but you see it's generally decreasing. But this sea level drops quite quickly, geologically speaking. So there seems to be some sort of non-linear response to climate to linear changes like in CO2. Okay, this is one of the scary things that geologists have seen in the past. Where we had the runaway greenhouse world at 56 million years ago. Even 12,000 years ago, there was a cooling that took place as we were coming out of the ice age. Okay, the climate's warming. And around 12,000 years ago, something got cold real quick, centered around North Atlantic. It was not a global phenomenon. And where over Greenland, temperatures decreased by about 8 degrees Celsius rapidly. And actually, we're talking about maybe within a decade. At least that's what the ice cores was showing us. So we see these tipping points, these nonlinear relationships in terms of where climate can change quite quickly, even though the things that control climate may be changing on a more regular basis. But when it comes to Antarctica, Antarctica has changed more than any other place on Earth. Okay? In fact, I would say that Antarctica is ground zero when it comes to past climate change. Where 50 million years ago was an ice-free continent. Okay, there was temperate forests around the coastline, no ice sheet, even in the interior. And then it's been slowly cooling to today, we have a polar desert where basically the ice really doesn't melt. It just basically falls off the edge of the continent, to put it in a simple way. There is a little bit of melting in the peninsula, but almost all of it is just falling off the edge. It's that cold. And so what I want to talk about now is the idea of how do we measure all this? I've been telling you things, about ice volume and this and that. Let me tell you on some of the methods. Well, on some of my graphs, I have a few terms that I just want to mention. First thing is called used to sea. If I say it, I just want you to know it. It just means global sea level. That's all. Apparent sea level is just basically a derivative of used to sea or global sea level that I coined a couple of years ago. And so it's on some of my graphs. And so I left it that way. Okay. So one way to do this is kind of simple. Ice volume, okay, the only mechanism that's both rapid and large for sea level changes is ice volume at the poles. Before 3 million years ago, there was no ice sheets for most of all intents and purposes in the northern hemisphere. So sea level was being mainly controlled by the size of the Antarctic ice sheet. And so what we can do is we can look at shallow water stratigraphy. So if this is the shelf here, okay, sea level's going up and down, and you take a core, you can, the sediments and the fossils that you see in those cores are very sensitive to water depth changes, to environmental changes, so we can actually start backing out global sea level. It's a little bit more complicated than that. I'll show you some of the caveats in a couple of moments. The other thing, I didn't take it out, okay, is we can actually look at oxygen isotopes, and and someone's going probably thinking, oh no, chemistry, no, I'll talk about it in a couple minutes. And then from deep sea records, from looking at shells made out of calcium carbonate from one-celled creatures, we can actually get estimates of ice volume from the deep sea. You're thinking, okay, and you have a bridge you want to sell me afterwards, right? But I will show you on how that's done. I was going to talk about some new proxies, but I'm not going to on this one. And then finally, of course, is the direct evidence. Going right to Antarctica, trying to figure out what is happening there. The problem with Antarctica, it's a big continent. And so my analogy is that it's like the blind man trying to describe an elephant. You go to one section, you get a piece of the story. The only way to do it is get a lot of records from Antarctica and then talk about it. And so the first one on a coastal shelf, we have the nice shelf here. Global sea levels going up and down. We also have sediment supply affecting it, as well as subsidence, which is due to loading. If you put sediments onto a lithosphere, it sinks. That's the loading component. Compaction, if you put sediments on other sediments, the sediments below will compact. And so we have these aspects that I have to model. I'm going to back out global sea level changes. And so the best place outside of the oil industry has been in New Jersey, in fact. Can you believe from Jersey? Can you believe it? And where we drilled many sites on the coastal plain, we drilled some out onto the shelf in here, and these lines here are actually seismic lines. Seismic stratigraphy is basically where we use sound waves to image below the sea floor. It's kind of like the sonograms of Mother Earth, in fact. And so we have the cores, we have the seismics, which are basically maps of what's underneath the sea floor that tie us in from site to site to site. And we drilled all these places, lots of work, got me my PhD. And this is actually a seismic profile. It's smashed here so I can fit it all in. And so it's like this is 20 kilometers and this is 1 kilometer. So you can see on how the exaggeration. But these lines here are actually sedimentary boundaries between the layers. Okay, so we're actually tying them in. And what we did is we drilled on land. Here's Atlantic City with the Trump Casino behind us. Okay, we didn't bet. Okay, so how deep is the Oligocene? No, we didn't do that. And then on the shallow shelf, we use a jackup rig, which is basically a ship that has poles go down to the sea floor, jacks it up, and then we can drill straight down. And then for the deeper parts, we use the JOIDES resolution. And so this is some cores. Unfortunately, the best ones I found were in black and white. This little gets an idea. This is from the coastal plain. So below it, we have some glauconite sand, and then we have this sequence boundary. The sequence boundary is just where sea level changed. Okay, went up and down. And basically glauconite, so we have shells and glauconite is a mineral that forms in situ, in the sediments themselves, and it's usually a deposit of forms in very low sedimentation environments. And so when we go out to the outer shelf, we go from this clay into this glauconite and all the way out onto this slope, we still see that same boundary. There's no evidence of shallow waters because this is the shallow water where we see oyster shells. And here we just see sediment starvation, just no sediments, just glauconite forming because there's just no sediments getting out there. And so what I do to back out the global sea level signal from the stratigraphic record is that I got to back out the loading effect, the compaction. So we do something called backstripping. It's an iterative process. You should do it at least 2-dimensional backstripping, if not 3. And it's this. And what we do is we unload sediments through compaction. So just say we have initial profile, we have a sedimentary layer A. We remove it, okay? Then we decompact the sediments below, where we can have understanding about porosity, and we can basically estimate, and through the modeling, understand on how much they would decompact if those sediments had never been there. And then we remove the flexural unload the flexural, because if there's no sediments, the lithosphere will pop up a little bit. Then we remove the thermal subsidence, because every lithosphere that's been rifted is still cooling, and so as it cools, it gets denser and sinks lower into the stenosphere. And then we account for water loading down in here. And we do this for each layer. We remove in the model each layer, and we go through this process. Result is that we got something cool. We can reconstruct the stratal geometry of the margin. So these lines here represent millions of years ago, 27 to 25.8 million years ago. This is distance in kilometers here, and this is just showing on how this shelf is building out through time from 27 to 25.8 million years ago. And we did this for the entire, from 34 to 22 million years ago, in fact. And I took out a slide because it just was too complicated, but at that point, the next step is to put our water depth estimates from the sediments and from the fossils into here, and then just watch on how the sea level is going up and down based on those estimates. And from there, we can back out global sea level changes. And that's what this is here. From 28 to 24 million years ago, this is in meters here. The blue is the best estimate. The error bar, the uncertainty, is shown in the light blue. And it's always good. When I was doing my PhD, I had a great advisor who said, be proud of your errors and show off your uncertainty. Because if you don't show off your uncertainty, you're wrong the moment someone comes up with a new study. If I say 80 and someone else comes up with 75, I'm wrong. But if I got a 10-meter error bar, I'm still right. No, I'm just joking. Okay. So anyway, so another way we can back out global sea level changes is from the deep sea. Okay, and we use shells made from one-celled creatures called fulminiferas. And if it's carbonate, we're talking about the chemical equation is CaCO3, O for oxygen, and we can look at the stable isotopes of oxygen. They're not radioactive; these are stable isotopes. Specifically, we look at them, the one that has 8 neutrons, and then a heavier one, the oxygen 18, that has 10 neutrons. And what happens is that when water evaporates, the lighter oxygen isotope, the oxygen 16, is preferentially evaporated, leaving the 18s in the ocean. And in fact, and then as the water vapor moves away from the tropics and the low latitudes, more of the oxygen 18s continuously rain out as rain, or at higher latitudes, snow, and enriching the water vapor with the oxygen 16s. Okay? And in other words, enriching the oceans with the oxygen 18s. And finally, when we get up to the high latitudes where we have ice sheets, the water vapor is so enriched in oxygen 16s when it snows out, the ice sheets build up with lots and lots of oxygen-16s, heavily enriched in oxygen-16s. The result is that the glaciers lock up and store oxygen-16s because they're enriched. And where did all the oxygen-18s go? They stay in the ocean, enriching oxygen-18s. So then we can take our little shells from the foraminifers, throw them into a mass spectrometer, get the oxygen 8, 16, and 18 ratios, and boom, we can figure out how much ice there is at the poles. Simple, right? We can go home now. There's a caveat, okay? And this is a problem. And as a matter of fact, even a 7th grade math student can figure it out, the problem. And that is that there's a temperature effect on the oxygen isotopes when they get precipitated into the carbonate. So we suddenly have two variables in one equation. 7th grade algebra, you can't do it, okay? So there is a caveat, so we got to make some assumptions and so on and so forth. Some new proxies that are trying to give us water temperature, but I took them out tonight because there's so many problems with them right now. I just didn't want to lie in front of you guys and say, everything's fine, we figured everything out. So we still have this problem, but we have ways to try to solve, we try to make estimates of the temperature to isolate the ice volume signal in the oxygen isotopes. So, and this is to some of the foraminifers. Aren't they beautiful? Aren't they cute? Okay, so this is, Cibicidoides species, and it has a constant offset in oxygen isotopes. This is Euvadrinus, and these are false colors, by the way. Okay, they're not that pretty. They're all basically clear white, but they are very nice. And then these are on the order of about 1/3 of a millimeter in size. 1/3 of a millimeter. Okay, they look like grains of sand. Okay, so when I bring students in for the first time, I go, you're going to look at these foraminifers, and they see the little grains of sand, and they go, so you went to Jones Beach, and I said, look under the microscope, and this is what you see. Okay, so this is the composite oxygen isotope graph. Okay, in a nutshell. Okay, to the right is warmer bottom temperatures and less ice. To the left is colder bottom waters and more ice. Basically, this is from benthic foraminifers, so these are the guys that live on the sea bottom. And one thing that you can see is that this is y-axis is millions of years ago, okay? And so it's really obvious. Here's today. The warmest period was from 50 to 60 million years, and actually when you get into the Cretaceous, when the dinosaurs were around, it was actually at least as warm as this, and you can actually see a spike right up here, those little dots, okay? These little dots here, those are real, okay? That isn't a little glitch there. That's where that we had that runaway greenhouse world at 56 million years ago, where water temperatures were in the low 90s off in New Jersey. Just imagine how much Trump would be sweating. But anyway, so we have very warm temperatures, a slow decrease over time in bottom water temperatures. Ice sheets probably start forming up in the plateaus in Antarctica. And 34 million years ago, bang, we go into the Icehouse World. Okay, the first time we had continental-sized ice sheets, probably in the last 250 million years, occurs at 34 million years ago. And then after that, it's basically a flat, there's lots of variability, but it's basically more or less stays constant, where we have this dynamic ice sheet in Antarctica growing to at least as big as today, and then collapsing to maybe, and I'll show you in a couple seconds, maybe to about half or a third of the present day. And then finally, in the last 3 million years, it gets much colder to today. And the last, where we have glacial periods and where we have glacial ice in the northern hemisphere. For the first time, probably in 300 million years, and it may be 650, that we had bipolar. And we had a unipolar from 34 million years, and then we went to bipolar. And I guess today we're in schizophrenia. Okay, I don't know. But anyway, just to kind of give you an idea, so just to back out a little bit, when values of around 2.1 oxygen isotopes, you must have some ice. And so we don't need to say that there's any ice from about 34 million years or older, but there probably was. Just little ephemeral ice sheets up in the plateau But after 34, we definitely have ice sheets, and it just gets worse. Values of around 3 per mil represent the fully glaciated Antarctic ice sheet. So you can see from 34 million years, during the glacial maxima, we see ice sheets that are probably reaching at least the full Antarctic ice sheet. And then finally at 3.3, that's similar to what we have today with the Greenland ice sheet, West Antarctic ice sheet, and having it really like a polar desert, or maybe an ice sheet bigger. Okay. Now, one last way we can try to determine ice volume is by calibrating the oxygen isotopes. So this is oxygen isotope amplitudes from events. This is the apparent sea level changes from my eustatic estimates or apparent sea level estimates, and calibrating the oxygen isotope records. And that was done a couple of years ago, and I think was able to dial out the temperature effect a little bit. So let's start talking about some of the results from ODP Leg, from Ocean Drilling Program legs. And this is millions of years ago. And these are from stratigraphic records, from shallow water records. And where the blue, or the boxes, represent sediments that are preserved. The red arrow, the red little wiggly lines, is when sediments were not preserved, and this is probably because of sea level lowering. And you see like a decent correlation between many of the sites. This is from near Australia, offshore New Jersey, Alabama, northwest Europe. And we see a decent correlation from site to site to site around the world. These dashed lines represent oxygen isotope increases. That's either bottom water cooling and or ice sheet getting bigger. And there's a decent correlation, and this has been shown from a number of records, from Miller et al. 98, what I did a couple of years ago. And this is what CO2 is like back then, in fact. Okay, so this is, we're talking about estimates maybe up to 1,500 parts per million, down to as low as maybe 300 or 400. These are the big error bars in here. And so it was fluctuating. So we had an ephemeral ice sheet. Usually it was not around. Maybe it would grow once in a while. So we would see these. And my wife told me to take this out, but I left it in anyway. Okay. She knows everything. But anyway, oxygen isotope increases. Shown here, this is millions of years ago. So these are big events where oxygen isotopes increase. And what I did a simple calibration, a comparison. I said, let's take two extreme ends. One where it's almost all temperature, the other one where there's almost no temperature involved in this change here. And what do we get? And so this is the average. So this is the average here. And we're talking about an ice sheet during this time period that was anything from nothing to an ice sheet equivalent to about 25 meters of sea level change. Today, the Antarctic ice sheet is around would be equivalent, if it melted, to about a 66 meter change. And so we're talking about, less than half. This would be about 2/3 of the ice sheet. This is how big it would be. And this is thickness here from numerical modeling from DeCanto and Pollard from 2003. So this is what we're talking about back then in 34 to 50 million years ago, perhaps. Now, once we get into the start of the Icehouse World, where CO2 is dropping from below 900 into 600, 500 parts per million, the ice sheet becomes a dynamic ice sheet, in fact. And I happen to be the sort of scientist who would rather debate something over a mug of beer than picking up a sword. And so what I did, is that I took all the papers that make estimates of ice volume, and during this time period from 23 to 34 million years ago. So this is the percent of present day Antarctic ice sheet, right over here. And this is the ice volume equivalent of changing it over to sea level. And what you see, I can't really see the light blue one, but you can see with the glacial minimum, this is where the error bars, and I love error bars because then everyone's right to a point. And so we had a glacial, so maybe 1/3 of the ice sheet, maybe half of the ice sheet, so it would retreat. But during the glacial maximum, for some reason the blue box is not showing up well here. Maybe if we kill the light, but anyway, yeah, thanks. Not that it's the most important point of the whole story, but it still doesn't do much. But anyway, you can barely see it there. And it looks like it's a little bit larger than today's ice sheet. And so you're probably going, oh my gosh, well wait, CO2 is anything from a little bit higher of today to maybe, much higher, so what's going on here? Well, the Antarctic continent was a much different continent back then. Well, even before I get to that point. The first point is that today, the Antarctic continent is so cold that the ice doesn't melt for all intents and purposes. It basically falls off the edge of the continent. It isn't like the Greenland ice sheet where there's significant melting before it reaches the coastline. Then on top of that, the Antarctic continent was a lot different. So this is reconstructed of the Antarctic continent, ice, removing the ice and letting the lithosphere rebound. Okay? Because right now the continent is sunk down probably anything from 500 to 1,000 meters in places because of the weight of the ice, because the ice is up to 4 kilometers thick. And so this dark area shows what the coastline would look like if all the ice melted and it isostatically rebounded the continent. Okay? Huge inland sea and the Ross Sea. Look at the Weddell Sea. Most of the West Antarctica is underwater for all intents and purposes. But what Wilson and Lundijk did is that they realized that they corrected for thermal contraction, a tectonic extension and thinning and subsidence due to that, as well as the incredible amount of erosion that took place from the ice sheets, basically bulldozing the sediments off the coastline. This is a reconstruction of the Antarctic continent 34 million years ago. The entire Weddell Sea fills in. West Antarctica is completely above sea level. In fact, it's quite high. This is a 1,000-meter contour line. The Ross Sea becomes filled in with elongate islands filling it in. And in fact, the continental area increases by about 15 to 20%, and the ice volume, because of the doming effect, would even be more. So having a slightly bigger ice sheet, even with elevated CO2, is okay because the continent was 15 to 20% larger than today, in fact. So it's okay. So to wrap things up, I want to end with an expedition that I was on in our winter of 2010. It was on the George's Resolution, 9 weeks just off the coast of Antarctica to look at Antarctic climate changes going back to 50 million years ago when the Earth was much warmer. So this is the Antarctic coast here. These are the different sites. I'm just going to talk about briefly because we're running out of time. These 3 sites in here, just briefly. This is the shelf here, and then going into the deep sea. And this is where we are here. This is the Ross Sea, Weddell Sea, and this is our sites here. So we were out there, we were pouring, looking at the sediments. This is the litho team, part of the litho, the night shift, I guess. This is actually Rob Dunbar from Stanford. We can play around out there. But the weather wasn't always nice out there. We were in the Southern Ocean, and we went from the roaring 40s to the screeching 50s. And so we had waves over 30 feet tall in some cases. And this is a good scene. This is from the official photographer. So take a look. He's up on the upper deck, looking at the bow, and you can still see the horizon. Okay? Take a look at this. No horizon, just the top of the wave coming in. And I'm the typical New Yorker. I want to see this stuff. And so they had a sign on this level here that said, "Do not go outside." So of course, I went outside. I don't follow rules. But I was way back here. I wasn't near the front, So I was way back, and I saw this, where the ship dipped down, and then the swell was coming up. And, I was fearing, I don't care if I get wet or die, but I just don't want to hurt my camera. And I remember saying to myself, I think I made a big mistake, But then the boat rides up, and then it just crashes over the bow, just like this. And, there was water that came down, but I was 60 feet down, so it was fine. But for the 2 or 3 seconds, the other thing that I said, if I drown, my wife's going to kill me. So anyway, But out there, there's natural beauty that's just, and in fact, I met a number of the scientists here, a few scientists who've been down to Antarctica, and Antarctica, at least for me, since I'm not an astronaut, it will be the closest I will ever get to landing on another planet. And I think that most of us would agree to that. And of course, there's the wildlife. This poor penguin, he's going out to sea, and there's probably a school of killer whales just circling him right now. Not a good sign, but, and then of course, there's the natural beauty, out there. So these are the cores that we did. This is showing in millions of years ago, and then these little cones here show what was actually recovered. So you can see, like for example, this whole big chunk from 34 million years down to 48 million years we lost. We didn't have any of it. But we did get a nice chunk of the start of what we call the Icehouse World from about 33.5 million years. And then we get a little hiatus in here. So we got some really good recovery in certain sections in this long core. The really cool thing is that we got down to 53.5 million years ago, right into the super greenhouse world when CO2 is over 1,500, probably around 1,500 parts per million. And one of the things that came out of this is we found, not we, some of the scientists, I didn't find it. I was looking for foraminiferous, and there weren't any. Boo-hoo. But they found pollen from tropical plants. Okay, this is not West Antarctica, which is much further north. This is at 67 degrees latitude. And they're publishing it, I'm not telling what species it is, but, because then they would have to kill me. But they're finding from semi-tropical plants the pollen. Okay? This is not because, some of you are probably thinking, I took Geology 101. Antarctica must have been away from the pole, near the tropics. No, it was still over the pole. It was because the carbon dioxide was so high, it kept the planet warm. And then we had some other cores that go back 13 million years here. We got a little thin core up here that actually got this little sliver at 33.5 million years. It's really tough out there. We had to evacuate certain sites very quickly, either because of storms or from icebergs. And these icebergs, you think that they're moving real slow, but when you're drilling a long pipe, you got to pull the pipe up. So sometimes you need hours to pull the pipe up, and you got to get out of the way of the iceberg. Because, as a matter of fact, the captain, it was his first expedition. He was always the assistant captain. And so, he was really wary. And I'm sure they was having nightmares. He goes, I am not going to be the captain of the Titanic 2. So one thing that we really got that was amazing is that we got a 200-meter thick core, almost over 100% recovery, and it only goes back 11,000 years. But we see annual banding, okay, bars from the bottom of the ocean, filled with microfossils, including foraminifers. So I'm working on it right now, actually, with Rob from Stanford, and we're going to be doing stable isotopes at 5-year resolution. Okay, I'm used to like 3,000 year resolution. That's great. And we're going to be doing other studies. And so you can see the annual, the dark and light, that's 1 year. Another year. Another year. Unbelievable. Core. And so there's a team of people, there's about 13 people, land-based and on shipboard. They're all working on this core, develop a great chronology, and doing everything you can possibly think that you can do to a core. Now, another cool thing is that after 14 million years, most scientists accept the idea that Antarctica got really cold and became stable. Went from that dynamic ice sheet I was telling you about to this cold, stable, polar desert-like. But then this paper came out, and it should have been in Nature or Science, but I guess because of the weak chronology, because of the age control weakness, it didn't get published higher. But they found, 300 kilometers inland, they found evidence anything from about 8 to 12 million years ago, because they didn't have good chronology, good age control, that the ice sheet retreated about 300 kilometers during that time period. They weren't sure exactly when, but it was sometime in that band. And we expected nothing like this. After 14, it's stable. Nothing's changing, because CO2 was near pre-industrial, and it didn't change much at all. So what the heck was going on? Meanwhile, we got a core. Great. This is age here. This is depth. Okay. This is the blackest recovery. So there was like 2 cores in here, another core here that we lost. But otherwise, it's like 100% recovery. And right in here, right in here, we got this really amazing core, and this is a blow up. So this is depth below seafloor, MBSF, and where we have there's no foraminifers, there's no calcite, no fossils from calcite, because it's just too corrosive, too cold of waters, and then suddenly, boom, at around 310 meters below seafloor, we get into a nanofossil ooze. Nanofossils are shells or organisms, basically like brown algae. They're autotrophs, so they make their own food, so photosynthesis, just like plants. And they live in the sea surface. They like warmer waters, and they make little calcite shells. But they don't like cold waters, and their shells can easily be dissolved in corrosive waters like in the Southern Ocean. And suddenly we start getting an ooze. So it's an ooze made out of nanofossils with lots of foraminifers, which I love, which I work on. And from 4 cores, for this, which is about 500,000 years or so, we have Antarctica, the oceans around Antarctica warmed up a lot. Okay? And that's what I'm working on right now. I have actually a graduate student working on this to figure out how warm did it get, what was going on there, and then link it back to that terrestrial site where they had the poor age control. We have great age control here. We see cycles every 40,000 years. We're going to have an incredible chronology here. And so just to wrap up, because it is getting late, is that some of the very early results, we drilled over 3,000 meters with about 2,000 meters of sediments recovered. The oldest sediments were about over 53 million years, and we found pollen from tropical flora. And we discovered this warm interval at around 11 million years. We got it well dated. It's about 11 to 11.5 million years. And so this is us crossing the Antarctic Circle, Rob and me. And it doesn't even look that cold because it's open ocean, so it's near freezing, basically. It's not too bad. I know for here that's very cold. But for New York, this is great. My jacket's open. It's okay, you know. And so let me just finish up with the future for IODP. I see lots of young people in the audience. This is one of the great success stories. I mean, you know, if an alien came down today, you know, I would not point them to reality TV or politicians as, you know, great success for humanity. But I would say organizations like NASA and SETI and ocean drilling has shown the best of humanity, where we're sharing, cooperating, working together, you know, removing that national posturing and so on and so forth. So we're going to be continuing on. There's going to be some changes because of budget constraints, just not in the United States, but also in Europe, as we're watching it unfold right now. But the idea is that in the future, these organizations are going to continue and develop. There's going to be lots of more expeditions in the future. With that, I'll take some questions. Thank you. Ooh.
Could I start with one?
Sure.
So the 1,300 parts per million excursion CO2 in Miocene or something.
1,300?
Did you say 1,000 or something like that? Some of the high excursions.
Oh, okay. They're like the runaway greenhouse world of 56 million years ago. Yeah.
What sort of causes are people thinking of for those CO2 excursions?
Well, like I said, it's not because the lemurs were driving around in SUVs. Okay, it was, in this case, it was probably volcanism and the type of volcanism, as well as the lack of the weathering of certain types of rocks. When you, like for example, when we uplifted the Himalayas and other mountain, some types of rocks, when they weather, they basically take out CO2 out of the atmosphere. Also, we have volcanism, which releases CO2, but it's also the type of volcanism. There was a nice study that was done, or an idea that came up, and it said, look, when you're doing subduction, and if you're subducting ocean plates where there's not much carbonate in it, the volcanism that you get is not going to release too much CO2. But if you subduct an oceanic plate that is carbonate rich, all that carbonate is going to get subducted, and it's going to let the volcanism release a lot more CO2. So it isn't the amount of volcanism, it can also be the type of volcanism, as well as weathering rates from uplift. I saw a question back there.
Yeah, I'll just go around.
Oh, okay, sure. Well, sure.
Hi, I sort of have the other end of that question, which is the 56 million year ago runaway greenhouse effect.
Mm-hmm.
Why didn't it keep running away and become like Venus?
That's a great question, and I'm not sure if I can really answer it, except that there are feedbacks. Mother Nature's got this amazing ability to try to rectify itself and hold itself in a certain climate mode. And what happened was that there was a flip. You know, the runaway greenhouse world, the leading hypothesis that we have today is that the Earth was already a lot warmer. It was probably about 4 or 5 degrees, maybe 6 degrees warmer than today. And then there was some volcanism that warmed it up a little bit more that allowed clathrates, which is frozen methane that resides on the sea floor, to start basically melting. And methane is a much more powerful greenhouse gas than CO2. It's probably about 23 times more effective. That methane went into the atmosphere, started warming up the atmosphere, and even when it breaks down to CO2. At some point, the way the hypothesis goes is that there was just no more clathrates to release. And so the heating into the methane release stopped. It turned into CO2. The CO2 then it gets absorbed by Mother Nature. Okay, basically by the ocean factory just absorbing the CO2, making it into shells and so on, organics, and sequestering on the sea floor, and it brought down the CO2, and so it stopped the greenhouse and actually started cooling it a little bit from that extreme condition. Great question. Okay.
One question is: Do you see any signature of solar activity cycle in the cores? And also, you showed the plot of going back, showing the relationship between CO2 and temperature and other parameters. And the question in the past, the CO2 was a consequence of the warming. Now we're saying the CO2 is driving the warming.
Exactly. Great. This is one of the great things that this is one of the typical things, and I'm so glad you brought it up. The idea, like you get on the Fox TV and they go, oh, if you look at the glacial cycles, temperature leads CO2, so it can't be the CO2, right? And any geologist who's taken my class, for past 101 geology, knows that the driver of climate over at the 20, 40, 100,000 year timescales is from those cycles I was telling you about. So that's the trigger. But the amount of change that can happen due to these changes in the shape of Earth's orbit and its axis is way too little to account for the incredible amount of climate change that we see from glacial into glacial. So the CO2 is the great enhancer, and those what I call geologically short-term timescales, 20, 40, 100,000 year timescales. It's basically it's those cycles, with CO2 being a great enhancer, plus other things like albedo, ocean circulation, blah, blah, blah. But if you go through what I was showing on the graph, those long-term millions of year timescales, and tens of millions of year timescales, you see CO2 higher, global temperature higher. And let me just say to you, I don't want to make it too simple because there's many factors in climate change, especially on these timescales. If you just look at those two variables, there's a nice correlation between CO2 and now we are basically, in terms of the climate system, we're basically throwing gasoline onto our fire. Okay, because CO2 is the great enhancer for climate. Yeah, great question. Thanks.
So one thing that I didn't follow is, what is it that gives you the chronology for the course?
That's because I never mentioned it. Thank you. There's so many things I could talk about. So what we look at are the fossils. The fossils are from organisms that existed at a certain time period, originated, and became extinct. And so the first step is, and this has already been calibrated from other scientists from decades and decades. So if we find fossil A, and we know that fossil A lived between, say, 34 and 28 million years ago. Good. So that's set up where we found it. It's got to be between those two, between that age. We find another little critter that lived from 32 to 20. Now we can narrow down to 30 to 32. And that's one of the using fossils. We can also look at we can actually look at the polarity signal in the sediments. Earth's magnetic field through geologic time flips every 500,000 to 1,000,000 years, okay? And in fact, it seems to be decreasing, and I've heard through, when you read on the newspaper that it may be flipping, okay? It'll still take 1,000 years or whatever to flip, but it's been flipping. The last time it flipped was 730,000 years ago. And it's like a barcode, where sometimes it's a long time of normal polarity like today, and then other times it becomes what we call reverse, which is where it's just the opposite of what we have today. Instead of coming up from the South Pole, it's coming up from the North Pole, the magnetic fields of force. And we could actually use that chronology. Once we have the fossils in place that narrowed us down to like a couple million years, we can actually look at the sediments, find where a polarity switch, and we go, look, it's got to be between 30 and 32 million years ago. The only polarity switch is right at 31.7. Boom. And so we can really fine tune it with the polarity. And then those are the two ones that we use on the ship. Okay. Oh, who's got the microphone?
I got it. I have a question for you. I'm, as you know, particularly keen about the preservation of polar carbonates in the cores that you find in the Wilkes Land.
So we've talked about it.
We talked about, it was about on the sea ice shelf. I mean, there was sea ice covering at the time that's supposed to be warming happened. And if so, were there forums associated with maybe sea ice so that the temperature might be?
From the sites that we have?
Yeah. What do you think?
Well, the site that I'm looking at, where I saw that little interval where the forams came in and then disappeared, it's actually hundreds of kilometers offshore. So there was probably no sea ice there. It's probably just too far offshore, or it was very ephemeral during the wintertime, early spring, or austral spring. And so I haven't looked at that. I've been looking at just using the stable isotopes to try to figure out what's going on with the climate and how warm the waters were. Yeah, but we could talk about it more. Yeah.
Okay. At the beginning, you showed a slide projecting CO2 levels by the end of the century to be anywhere from 500 to 1,000 parts per million. I wondered what assumptions went into that, particularly regards Earth's population and so on.
Well, this is not my forte. This is from the IPCC. Okay, the Intergovernmental Panel for Climate Change from 2007. But the scenarios are basically they're looking at if society gets its act together to start reining in CO2 emissions. I'm sure that they factored in population, also the amount of resources. We're going to run out of oil. Okay, I could have showed a slide where you see CO2 going up, and at some point the CO2 starts dropping in terms of emissions because we're just going to run out of oil. Okay, and petroleum, and so I am not an expert at that, but I'm sure that they put in all those factors. Yeah.
IPPO, thank you.
Yeah. But do we?
No, the questions are this.
Oh, okay. It's getting a workout.
Yeah.
Oh.
There are no further questions.
Oh, no, there was one more.
There's one down here.
Okay.
You mentioned in one of your report, when you've done an analysis, you'd actually determined that a radical change, I believe it was in temperature, happened in a period of like 10 years.
Yes.
Has anyone started developing theories as to how that might have happened?
Yeah, what he's talking about is, remember I talked about that regional climate change that happened in the North Atlantic that affected mainly Greenland. It happened only 12,000 years ago. It's called the Younger Dryas. Because what the European scientists were seeing as we were coming out of the glacier, they were looking at the lake sediments and they saw this tundra flower called the Dryas flower. And then it disappears because the climate starts warming up and they're going up through the lake bed, and then they see another episode, very short, about 1,000 years, where this Dryas tundra flower comes back. So they called it the Younger Dryas. Now, the leading idea on how this happened is that as the ice sheets were melting, lots of meltwater from the ice sheets got bottled up behind the ice. And at some point, it released in a catastrophic way into the North Atlantic, freshening the North Atlantic. Now, as many of you probably know, we know about the ocean circulation where the Gulf Stream goes up, heads up northward, bringing lots of warmth, and as it brings warmth, it's also evaporating, becoming more dense because it becomes more salty, cooling, making it more dense, and at some point, past Iceland and Greenland, or near Greenland, it gets dense enough that it sinks all the way to the bottom, okay, and becomes bottom waters. The result is that we get this nice conveyor belt of warm waters going up and warming northern Europe. That freshening basically made the waters not dense enough to sink down. So it shut off that circulation pattern, allowing the Gulf Stream to basically, instead of going up north, just to turn eastward. Yeah.
So you said that the CO2 now is designed to have been for a very long period.
3 million years, approximately.
And is the time resolution, how good is the time resolution? I mean, is it possible to say that the CO2 never went above that, or is the time resolution such that it could have for some short length of time?
Excellent question. We don't have the proxies that we have. Yeah. Up to 800,000 years, we got the ice cores. We just take a little bubble, we can get as many readings as we want. In this case, the proxy is new, the resolution is lower. It could have been, before 3 million years. I'm not an expert at that, but as the resolution is increasing, and it looks like it would have been pretty hard pressed for it to have been higher than, significantly higher than 300 parts per million between 800,000 years and 2.5 million years ago.
You can certainly say that for the ice cores from the Antarctic and from...
Oh yeah, 800,000 years ago, we got it, for sure.
Just one quickie. On all these assumptions and everything else, has essentially the radius or the diameter of the Earth remained constant in your calculations, or have you made allowances for changes in that?
I have never heard of that, the changes in the radius, so I couldn't speak to that.
If there's no further questions, I'd encourage any of you who have burning questions that you just can't ask in public, feel free to come up and ask Steve after the talk. Steve, we have a SETI mug.
Thank you so much.
In commemoration of your talk, and please join me in thanking Steve.